All right, let's take a look at this. So we can think of this in two ways. We can still try to shoehorn it into a conservation of energy problem, or we can take a step back and say, well, where did conservation of energy come from? Where did it come from? How did I get to this equation? I said, well, work equals the change in energy, and if we decide that the work on a system is 0, then 0 equals the change in energy, so the initial energy equals the final energy. Right? So I can start back at the very beginning and say, well, let me rework my work equals change in energy, and say, work, therefore, equals E final minus E initial. Right? Where E final can be potential and kinetic, and E initial can be potential and kinetic. Right? So let's do it from that perspective. So where does my 5 joules go from that perspective? If we're going to use this guy, work goes on the left. Now we have to be careful. How much work was done on that system? What does it mean? How much energy went into or came out of the system? Did 5 joules go into or out of the system? Came out. So how do we show that it came out? We have to say that the work was negative 5 joules. The system lost 5 joules of energy. All right. What does that equal? It simply equals the change in energy. So E final is just 1/2 mv final squared plus mgh final minus the initial, which is 1/2 mv initial squared plus mgh initial. Now you may notice this almost looks like the conservation of energy, right? If I just took my initial energies and I added them back over to the left-hand side, I have initial energy equals final energy. But I still have that little negative 5 in there. What did that mean? Well, if I added up my initial energies and I took 5 joules away from that, that's how much energy the system ends with, right? So that's where this conservation of energy and work energy kind of really come together and intersect. I can still think of it from the perspective of conservation of energy. I just have to say whatever energy I begin with will be reduced by 5 joules as this system proceeds, and it will end with some new amount of energy, and the energy can always be stored in 2 different ways. Right? So you could have kept going with the conservation of energy and said, well, now I'm just going to lose 5 joules from my initial energy, and you could have just thrown in a minus 5 there. So you can think of it either way. All right, so what do we want to call 0 for my height? All right, let's do Bailey's way, because Bailey always gets his way. And let's say that this pendulum bob, where it starts, 1/2 meter above its lowest point, let's say that is 0. Okay, so what does that mean, Bailey?
It means there's no potential energy at the start.
No potential energy at the start.
No kinetic at the end.
There's also no kinetic energy at the end, which would have been the case regardless, right? And I'm looking for my final height, right? So H final. If we take a look, can I just divide out all my masses and get rid of them?
No.
No, it's not quite that simple, right? Because I've got this 5 in there, and so when I divide the masses go out from everything, but I get a negative 5 over M. Right? So it's up to you and how you want to solve this. I'm going to have to divide masses anyways to get H final by itself. Now I'm really just dividing M times G. Right? So it's going to be the left-hand side over mg, 1/2 mv initial squared, plus my negative 5, right, divided by m times g. All right, so when we plug in 1/2 mv initial squared, that's going to be how much? It's the same as it was over here, except now I have the mass. I gave you a 2 kilogram mass. All right. So 12.5 times 2 is 25, minus my 5 joules, so there's where the work comes in, so I'm left with a numerator of 20 joules, and my denominator is 20 joules. So I get 1 meter. Let's remember what that means though. What does that mean? 1 meter. 1 meter above what I called 0, which happened to be the initial height. So relative to the bottom, if I chose the bottom as h equals 0, what answer would I have gotten? 1.5 meters, right? Let's check our answer. Does that make sense? My final height would be 1 meter above where it started, whereas before, when no work was done, my final height would have been 1.25 meters above where it started, or 1.5 above the bottom and 1.75 meters above the bottom, right? So if air does work taking energy out, obviously the pendulum's not going to swing up as high as it would have otherwise. All right? Questions? All right, so the important thing to remember is this is the same analysis that you're going to do with your roller coasters. It's just a different type of system.